Hello, mathematicians. We are going to continue our discussion of functions by talking about bijections. In previous videos, we learned what a function is. We learned that a function could be one-to-one, or onto, or both. If a function is both one-to-one and onto, it is considered a bijection. Okay? So remember, in order for a relationship to be a function, every element in the domain must map to an element in the range. Just one, exactly one. Now, it is perfectly fine in a function for two elements in the domain to map to the same element in the codomain. But if a function is one-to-one, every element in the domain will map to its own element in the codomain. And for a function to be onto, there are no leftover elements in the codomain. The range and the codomain are the same. In other words, if you select any random element in the codomain, there is some x value that maps to it. Let's look at an example. It says, consider a hypothetical country Z in which every person is married to at least one other person. There are no singles. Everyone is married to at most one other person, so no polygamous or polyandrous. Every marriage is between a man and a woman, so there are no same-sex marriages in hypothetical country Z. Again, just for the sake of this example. We're going to let men equal the male inhabitants of Z and women equal the female inhabitants of Z. Then the wife function maps every man to his wife. So that maps the set of men would be the domain. The set of women is the codomain. This function, the wife function, is a bijection because two different men cannot have the same wife. So we know that wife is a one-to-one function. Every woman is the wife of some man because everyone is married. So wife is also onto. Similarly, we could write a function called husband, where the domain is the set of all women and the range or codomain is the set of all men, and it would also be a bijection. In the country Z described above, it is clear that the number of men is exactly equal to the number of women. If there were more men than women, then not every man could have a wife. If there were more women than men, then not every woman could have a husband. This is an example of the following important principle. If A and B are finite sets, and there exists a bijection from A to B, then A and B have the same number of elements. Finding a bijection is one way to show two sets have the same number of elements. Proving that a function is a bijection. Since a bijection is both one-to-one and onto, a proof that a function is a bijection usually has two parts. We show that the function is one-to-one, and we show that the function is onto. The two parts can come in either order. It is perfectly acceptable to first prove that the function is onto, and then prove that it is one-to-one, or vice versa. How would you show that a function is not a bijection? You guessed it, by counterexample. You only need a counterexample that shows either the function is not onto or it is not one-to-one, because a bijection requires both. Let's take a look at this example of function f. We have the closed interval from 1 to 3 as our domain, and it maps to the closed interval from -2 to 8 by this rule. And so we want to show that f is a bijection. It suffices to show that f is both one-to-one and onto. So we begin showing that this function is one-to-one. And so what we do is we select two arbitrary elements in the domain that map to the same element in the range or the codomain. And we show that that must mean that the two elements in the domain are the same. So this is a great way to show one-to-one. We say x sub 1 and x sub 2 are elements of the domain. This should really say the domain, such that f of x sub 1 is equal to f of x sub 2. And what we want to show is this must mean that x sub 1 and x sub 2 are the same element. So what is f of x sub 1? What is f of x sub 2? Well, we go back to the rule. We substitute those in. By algebra, adding 7 and dividing by 5, we will find that x sub 1 must equal x sub 2. So this means f is one-to-one. Because if two different elements in the domain map to the same element in the codomain, then those two elements in the domain must have been the same to start with. Now we show onto, and we begin with an arbitrary element in the codomain. We carefully construct our x value such that when we substitute that x into the function, we get our y value. We must verify that every y is in the codomain and that x is in the domain. For every y that's in the codomain, x is in the domain. So we begin with the restrictions for y. If you add 7 to each side, you come up with this. If you divide by 5, you have this. This means that x is confined to the closed interval from 1 to 3. So f is onto, because that was our domain. Since f is both one-to-one and onto, we conclude that f is a bijection. Now, you're going to get lots of practice proving that a function is one-to-one and onto. And of course, that means you'll also get practice discovering if something is a bijection or not. Use the examples that you've been given as templates to construct your own proofs. Reach out, please, if you need assistance.